Thanks. So yes, so dimensionality is always a problem in optimization?
It depends. It depends on the algorithm. The examples I gave here are using specifically a very naive and silly method, which is to go evaluating point after point after point on a grid. And to find the global optimum with this method would take you trillions of years for a big problem. We're going to see some numbers in a plot later. So it depends on the algorithm, okay? So for combinatorial problems where you actually have to somehow enumerate, or even by implicit enumeration in the algorithms we're going to see, the growth in the number of variables, yes, does affect you badly because we don't have any way to break away from them unless you somehow magically have a quantum computer that can solve the combinatorial problem in no time. But with conventional algorithms like this, combinatorial problems will suffer if the algorithm is of combinatorial nature. But for problems that are smooth, like the convex programming problem, whether linear or nonlinear, then there the complexity is always going to be polynomial in the number of variables. So it's not necessary that it's always a problem. It depends on the formulation, what class it belongs to, and what types of algorithms are available to address it. And of course on the individual, on choosing the right algorithm rather than complete enumerations. But we take out the individual from this equation. So, is there any more discussion on this that anybody would like to make? Okay, so the second aspect of the curse of dimensionality has to do, so the first bit was like, I have a function in many dimensions, what if I did complete enumeration to solve it? The answer is bad answer, okay? You don't do that. What about constraints though? That's the second aspect of the curse of dimensionality. Let's look at a two-dimensional feasible region, meaning that your variables, you have a problem with two variables, x1 and x2, and you're only allowed to take values from this odd-looking red shape, which is my feasible region F. No value outside it is allowable. And perhaps that's because of the modeling equations you have, but they restrict you to being here. It is difficult, and now I'm going to, I wouldn't want to use the word debunk random search methods because they have some utility, but it's good to know the limitations and use them appropriately depending on what we're trying to do. So this is again going to be a bad example of how to use random search methods. So it's difficult with random sampling methods to get a point within arbitrary feasible regions. Why? Let's start with this. Find an outer bounding box containing your region. So for this region, somehow, which is not a trivial thing to do, but anyway, I have this box, x1 and x2, which contains my feasible region. And then what I'm going to do is sample points uniformly, because I don't know any other way to do it. There's no probability distribution function that I could use that would mainly generate them in here, unless there's a special property. So you generate points in this square, the bounding square, and you try to see whether a point has hit the constraint, it's inside and satisfies the constraints, in which case you accept it and evaluate the objective, or if it's outside the constraint feasible region, you reject it and you take another sample. So, if the point is feasible, the randomly generated one in the uniform square, and if it improves the objective, you keep it. Else you pick a new random point and go back to step one in trying to improve your objective function. Will this algorithm work for any dimensions, is my question. And your answer is?
Yes.
Why?
Yes.
We have a yes. Why will it work?
If it happens to sit on the optimal point, then I think.
If it does, but will it be as easy as in 2 dimensions or 3 dimensions or 10,000? And the answer why, you can sketch it in a simple way. For simplicity, let's consider that the feasible region is actually a square itself, the yellow square F. And that I found a bounding box, it should have been itself, but I assume I don't know. So, which has side S, the bounding box has side S, whereas this square here has side S minus epsilon. So it has equal distances from it, and it's centered in the outer bounding box. So it's bounded within an outer square sampling box of side S. The probability of finding a point within the inner square, the yellow one, is equal to the ratio of the 2 hypervolumes. So it's S minus epsilon to the n, which is the hypervolume of the inner yellow square, divided by the hypervolume of the outer square. You do some simple algebra here, and epsilon over S is always going to be less than 1. I may even assume that it tends to 1, but it's never 1. And what happens here, as you increase n, the probability of finding a feasible point tends to 0, exponentially. So again, it decays exponentially, even if your bounding box is very, very, very tight. Higher dimensional objects, this is the conclusion also here, which is correct. From higher dimensional geometry, higher dimensional objects have all of their volume concentrated near the surface in higher dimensions, which is true in other dimensions as well. A square has less volume area near its perimeter than volume of a 3-dimensional cube. And this becomes very pronounced when you have a big N. So you'll never find an interior point in the feasible region the more variables you have. So I plotted some numbers here. For epsilon over S equals to 10 to the minus 3, which is very tight for the squares, we obtain the following figure. For example, for n variables, 10,000 variables, which might sound a lot to you, actually it's not. That's a typical kind of flow sheeting problem. It could have more than that. The probability is so many zeros, 45, to find a point that belongs into the feasible set. So again, finding therefore a single feasible point requires an exponential number of trials. Now, generating points within a convex feasible set is generally not so much of a problem. It is easy if the problem is defined by convex inequalities. You can generate that rather easily. Randomized methods may work, and generating though points in non-convex sets can be an issue. So in general, the conclusion out of this is that random search methods are not really always guaranteed to give you what you expect, and it depends on the dimensionality of your problem quite severely in an exponential fashion. Which brings us to the third question. Okay, so you told us that everything requires lots and lots of function evaluations, and these methods are not so good for certain class of problems. What about if we had faster computers? And I would answer back with a question, and I would say, how fast can you build a computer to be? And let's see the answer. So computer chips double their speed, in actuality the number of transistors, and therefore the number of operations they can do per second, every roughly 2 years. And this is what's become known as Moore's Law. And I just took this picture from Wikipedia. This is the transistor count of a chip. And this is the year of introduction of that particular chip, counting from 1970 until 2017, roughly, I think. And you can see that you have almost a linear slope for a least squares line to go through them. And the slope is like doubling, and this is a log scale, so it kind of doubles every 2 years. Now, forgetting that there might come a saturation point, which is predicted around this time or in a few years' time, doubling the speed of a computer every 2 years for an exponential complexity problem of 2 to the n operations, let's say it's only 2 values and n variables, this means that we will only be able to solve a problem of n plus 1 variables in the same time that we solved the smaller problem 2 years before. Because you double the speed of the computer and you ask the question, by how much have I increased my capability of addressing a bigger problem? And the answer is by just 1 variable. So again, the answer comes here. If you're dealing with combinatorial complexity and your algorithm is bad, i.e. combinatorial complexity itself, then you won't be able to solve it. As we will see, there are fortunately special algorithms to deal with classes of combinatorial problems. Are there any questions here? Yes?
Oh, I'd love to ask a question here. I got into trouble with a computer engineering guy over a college dinner when I mentioned Moore's Law. And he gave me a nasty look and told me it finished ages ago. And then we had a discussion about what it means. So is it number of transistors or is it number of transistors per dollar in a unit area? And so eventually he agreed with what you showed there, that okay, so per dollar, you've still got this improvement going on. Also we said it's partly a self-fulfilling prophecy. That basically it's just a design target for people to bring out next year's chip, which is playing against the mass. We could do better if it weren't for the fact that it was so painless. But the third thing I was going to say was that philosophically, this Moore's Law of growth is not very helpful for us because we have to wait years. It's great for people who are going to live in the far future because they'll have a pocket calculator that can deal with 200 variable problems if they want it to.
Also, depending on your algorithm, you can turn it a little bit around and make the following statement. Depending on your algorithm, hopefully it's not of combinatorial complexity. Let's say it has some polynomial complexity, but it's too slow with current computers. Then you shouldn't be discouraged from thinking that your result is not good enough in research, because in 2 years' time, in 4 years' time, you'll have a 4 or 8 times faster computer, and what seems now to be too much, 60 minutes of computational time, in 4 years' time, it will be 6 minutes, or 8 years' time. So as long as you have that in mind, and you're doing research in algorithms, etc., you should also not be discouraged by wanting everything here and now. If it's combinatorial complexity, exponential, then that's another ball game, and I would agree that it's forever a bad problem. Okay, now having sort of seen the generalities and set the background, I'll start talking today about these, and we'll finish, I don't know, in 10-15 minutes and continue on Friday. I'm going to talk about generalized optimization formulations. So the nonlinear programming problem that was introduced on the first slide sets the general format of what will follow. the scope of optimization models can be widened to capture problems of significant interest in industry as well as in research, and not just in chemical engineering but across disciplines. So the first one that I want to start with is what I spent my time of my PhD doing, which was to try to solve optimal control problems, or OCP. This is the case where we are looking for control functions. State responses are also functions, or the input and output of a system. And this is an infinite dimensional optimization problem. Why? Because a function is defined by an infinity of points in the domain of interest, and therefore it leads to what's called here infinite dimensional. And it's best understood by example. And I'll give you a chemical engineering example. Consider that you have a plug flow reactor, tubular reactor, which you want to design, and it's in hydrocarbon processing. And some reactions are taking place inside the tube, and you want to maximize one of the reactants at the exit. However, different reactions are catalyzed differently depending on the type of catalyst you're using. And in this particular case, you know that you can achieve these reactions by using two catalysts, either one or the other, or a blend. And the outcome might be different depending on the compositions. Or in other words, where you are in the tube along its axis. So the task here is to find the optimal catalyst blend along the length of the tube in order to maximize the yield of a desired product at the outlet of the reactor. So this is what it looks like. This is your reactor. You have the inlet stream with the feed. You have a distribution of catalyst fractions along the length of the reactor. And what you want to achieve with this distribution is to maximize your desired product at the outlet. And the question is, how on earth am I going to find this? It's not a single value like I introduced so far. It's not a single, it's not a value, a real variable that says 0.99 or 0.75. It's a different value at every point along the reactor. And the easiest way to actually deal with this problem in engineering practice is to use parameterization so that you render the problem from infinite dimensional at every point in the reactor into finite dimensional. You either parameterize the control functions only, which is called control vector parameterization or feasible path method, or go extreme and parameterize both the controls and the concentrations and the temperature and render everything into a large set of algebraic equations, huge set, which you optimize using what's called the simultaneous approach. So basically this is what you do. If this is your length of the reactor, let's say from this point to the end, I break my reactor into 4 segments in which I may assume I have a fixed composition and optimize just the level of segment 1, segment 2, segment 3, segment 4, or I may assume that I have a linear variation, or I may assume that I have a quadratic or cubic variation or splines, anything you want, to approximate the actual true solution, exact solution of this problem. And that's how you solve optimal control problems in practice. And this, if you use collocation, for example, you would discretize your reactor into finite elements. Within each element, you would have individual points where you evaluate your model. This is just a Jacobian view, but effectively what this results is in the following. If you have a flow sheet and you discretize it at every point in time, let's say, that you're optimizing, it's like creating multiple instances of the equations of the model for each point you discretized your model at. So the more discretization points you add, the size of your problem grows tremendously. But you can still try to solve it. And what does a formulation look like for an optimal control problem? You will have differential state variables, x. You will have potentially algebraic variables. Differential variables are usually compositions, temperatures. The algebraic variables are usually physical properties, kinetic constants. The control variables could be anything you regulate, like feed rates, heating rates, reflux ratios, and things like that. You may have also time invariant design parameters. Notice that these are functions of time. These are not, and they could be, for example, the size of a vessel, or the number, I don't want to say the number of trays in a distillation column because that's a discrete optimization problem, but it could be that. And finally, you may also be optimizing the process time, because your model being dynamic, it might correspond to a batch process. So how long should I run the process to maximize my product? And it looks like this, which basically is just a fancy way of saying it's a function of all the previous things. The model is a differential equation, which is a function of all the previous things. The constraints, functions of all the previous variables, and so on and so forth, plus initial conditions. And it keeps going on. You may have now bounds, because what are you doing? You're choosing controls, which are degrees of freedom. Your optimizer somehow has to give you these functions, and they're bounded above and below. The design variables may have upper and lower bounds, and the process time the same. It should be upward here. So that's one type of problem, an optimal control problem. The second type of problem we may face, or class of problems we may face, is that is the case where we have more than one objective function. And you might say, how can you have more than one target in the same optimization problem? You can, but that in effect is calling for some kind of compromise, which we'll see how you do it. So multi-objective optimization deals with problems with at least two objectives. So it can be bi-objective, tri-objective, or just general multi-objective. The multiple objectives have to be optimized simultaneously, and they are always conflicting performance indices or targets for a given design, the same design. It could be that you have to maximize the profit while you minimize environmental impact, while you minimize also risk for your workers, for damage to the equipment, and so on and so forth. So you can see that these play against each other. If I want to maximize my profit, I'm going to make sure that I don't invest anything at all to protect the environment, or I don't care about the risk to anybody. Conversely, if I want to make it totally environmentally friendly and have zero risk, I'm going to never go ahead with a design, because that's part of human life. You do something and there's always a risk. And the question is to balance it in a rational and correct way, so that you know exactly what's happening. So how does it look? It looks like this. You have a vector of objectives, which is to be minimized. It's hard to say minimize a vector. It means minimize this and this and. Subject to the model equations as we had them in the very first slides of the presentation. Now, the value of the objective vector F star is called the Pareto optimal after, I think he was an economist, Pareto, who came up with this equilibrium of conflicting objectives. A Pareto optimal is such that there does not exist another vector F, objective function vectors, such that Fi, one of the objectives, is less than Fi star, this should have been star, for all the objectives. And all the others, at least one of them, is less than, is strictly less than the optimal. It does not improve at least one objective while the others remain at least the same. So this is also called a non-dominated solution. So solution cannot be dominated. This is best explained. Yes?
I just wanted to ask
Yeah.
a question about the term Pareto optimal. So
Yeah.
if you have a point that is significantly better in one variable, but only a very, very small amount in the other variable, are they both still considered on a Pareto front?
Both better. So if I were to draw your
Say
objective.
you had two objectives, yeah.
Okay, so I have F1 here and F2 here.
Yeah, and say you had a very high
So
value.
here is my first point, A,
Yeah, and in the other value, B is very low in F1.
low in F1, so it's in this direction.
Yeah, but a little bit higher than A in F2, but only a small amount higher. So a lot lower in F1, but only a small amount higher.
Like here.
Yeah. So you could say they both lie in the Pareto front, but your A is still a better point.
No, it's not.
Because you're a lot better in one variable.
That's qualitative.
Okay.
You cannot say it, because if they're both on the Pareto front like this, then they're non-dominated.
Okay.
Because one has improved a lot at the expense of another, by little. It's still Pareto, strictly speaking. And we'll get into that. It depends